Good afternoon, and welcome back to the. This week we have Dr. Christopher Berry giving a course on compact binary evolution rates and population modeling. Christopher is a lecturer at the University of Glasgow in the UK. He did his PhD at Cambridge and was a postdoctoral fellow at University of Birmingham. And then was a research professor at the Northwestern University before joining the faculty of University of Glasgow. Christopher's research interests involve the astrophysics of compact binaries and compact objects in general, and their observation through a variety of astronomical observations, in particular using gravitational waves. Apart from producing a large body of very important work in gravitational wave astronomy, he is playing a very active role in the LIGO-Virgo collaboration. He is one person responsible for producing several of the flagship results from the LIGO and Virgo collaboration. He has also played several leadership roles in the LIGO collaboration, has been a member of the LIGO's program committee and was a member of the editorial board, probably still is a member of the editorial board. We're very excited to have Christopher, one of the leading experts in this field, giving this course on compact binary evolution rates and the inference of the population properties. This is one of the hottest topics in gravitational wave astronomy, and we are very fortunate to hear from one of the experts in this field. So without any further delay, let me hand it over to Christopher.
Thank you very much for the kind introduction. It's a pleasure to be here. And yes, I'd like to talk to you over the course of the coming 5 lectures on how we do compact binary astrophysics with gravitational waves. So in the course of this lecture, we're going to touch upon several different topics. Each one of these is highly detailed, so we won't have the time to go through these fully, but hopefully enough to give you an overview of the basics of these and, importantly, how they all fit together to tackle the problem of how we understand what is going on with the evolution of compact binaries. So this is binaries made up of compact objects such as black holes and neutron stars. So the idea is that we're going to start off first couple of sessions talking about the astrophysics of compact binaries. We're going to talk a bit today about why we're looking at these binaries, why they're good to observe with gravitational waves, and the types of way that we can make observable compact binaries, so binaries that actually merge and so can be observed with gravitational waves. And then next time we're going to delve into a little bit more some of the physics behind the formation of these. There's a large number of uncertainties in the astrophysics of the formation of these channels. This is perhaps a challenge if you're interested in making predictions because there's so many uncertainties. But if you're interested in the other side and going from observations to constrained theories, this means that it's an extremely profitable field that since so many things are uncertain, there's a huge amount we can learn from the data. So in the second part of the course, so in the 3rd and 4th lectures, we're going to talk a bit about gravitational wave data analysis in the compact binary coalescence case. So when we have a binary that's merging, how we go about data analysis here. In the first one, we're going to have a brief overview of data analysis, the various stages that we go from having raw data from our detectors to constraints that we can use to understand binary evolution. Key to this is what we call population inference, and this will be the subject of the 4th lecture. We'll go through the mathematical formalism of this quite a bit, and this population inference is the task of when we have a population of observations, what can we infer using them all together as an ensemble? So not just considering one event at a time, but all together, what can we learn about the underlying astrophysical population given this set of observations? So at that point, hopefully you'll have a bit of idea of why there's a lot of physics involved in compact binary astrophysics, why there are many possibilities for the different formation channels, where some of the key uncertainties are, how we get from our gravitational wave data to some measurements of the source parameters, and then how we loop that all back together to go, okay, given this, this set of observations, what can we map back to the astrophysics and understand about these sources? So to round off the course in the final lecture, so third part of the course, fifth lecture, we're going to take a look at current results from the LIGO-Virgo-Cagra collaboration, what they have taught us, and some remaining questions about them. And hopefully that will give you some ideas about what you might like to do if you're continuing in research in this type of area. Okay, hopefully that makes sense as a broad overview. Hopefully not all of this is stuff that you've heard before, so there will be new things to ask here. So what I would really like to do for this lecture course is make this a bit of a conversation, a bit of a discussion about the things that you're interested in. So we're trying to adjust the structure of the course based on questions you have and things that you find interesting. So if you do have questions, please put them in the Zoom chat, put your hand up, or I guess try speaking up if we can keep that to a manageable level, and we can discuss things live there. And rather than going through a lot of slides, I'm going to try and do this similar to how I would give a Blackboard talk if I was in person. Sadly, not being in person, we're going to try and do this the old-fashioned way with some paper. So we're trying to adapt this as we go on. So if you give me some feedback, that would be really useful. And yeah, we'll give that a go now. But before I get started, does anyone have any questions or just like to try out some question asking? Everyone seems shy so far. That's okay. Yeah. Oh, go ahead.
No, we don't see any questions yet.
Okay. Now, can you see my piece of paper?
Yes.
Okay, so let's get started. We're talking about compact binaries. Why are these so interesting? So we're going to have a
full screen that.
So why are we talking so much about compact binaries? So let's talk a little bit about what makes a good gravitational wave source. So can anyone tell me gravitational wave strain, which we'll call H? Do you know what we need to have for a source for a gravitational wave? We need a particular varying something. Does anyone know what that is? Okay, so gravitational waves are sourced by something. What is the source of gravitational waves? So we want to write down H depends upon something. It is, I know this is something that you did cover in the last lecture series, but I know that was perhaps mass. Yes.
So you can have a second derivative of the quadrupole moment in the leading order.
Fantastic. So yes, the mass quadrupole moment is what we're after. Let's call that Q. And as you say, it's the time varying of this second order. So it's Q double dot. So we've got something which is going to be proportional to Q double dot is our gravitational wave strain. Okay. What else do we know about gravitational waves? Well, we know that the amplitude will scale inversely with the distance from the source. So luminosity distance, let's call that R. So if we put those together, we have Q double dot over R. So this is the source of our gravitational wave strain. So if we want a good gravitational wave signal, we want H to be as large as possible. So ideally, we would want a source as close as possible. However, as we will see, we're talking mostly about astrophysical sources. So we can't really control the distance too much. So it's really now thinking about Q, the mass quadrupole moment. So let's think a little bit more about what Q double dot would be like. Well, let's taking time derivative twice. So if this has a characteristic frequency associated with it, that will be something like frequency squared times Q. over r. And what does the mass quadrupole look like? Well, it's going to be something like the total mass times the size squared. Okay, something like this, you know, going to be some constants out the front, and it would depend on the exact geometry, but it's going to be something like this. So we see that to have a good gravitational wave, we want something massive. Okay, so this implies why we need the astrophysical sources. We want things many times the mass of our sun, ideally, and we want to be varying as quickly as possible. So we want as high frequency as possible. Okay. So this can be problematic because we also have this size here, and typically frequency and radius go inversely with each other. That if you make something bigger, then the frequency goes down because it takes longer for anything to happen. So we have a balancing act between sources here. So generally compact object, something like a black hole, very massive, which is good, and we want it to be moving very quickly so we can have that frequency. Okay, so let's take a moment now. We've got our proportionality here. This is some approximate astrophysics. As we're going to see throughout the course, a lot of the astrophysics to do with binary evolution is uncertain. So we do need to make some approximations for going on some simplified treatments. So we're going to start off, give you just a bit of a flavor of this, and work through some dimensional analysis, which is a useful tool just to fix up what the form of this equation should really be like if we put constants in here. For this type of problem, we're talking about a problem in gravity, we're talking about a problem in relativity. So we know there are potentially some factors of G, Newton's gravitational constant, and C, that's speed of light in a vacuum, which will also be the speed of gravitational waves, that we can potentially put in. And we can work out what powers they are by looking at dimensional analysis. So if we take a look at our equation, we have a gravitational wave strain, okay, which should be dimensionless. It's a strain, so it's a length divided by a length, so this should have no units, it should be dimensionless. And on this side, we have f squared m r squared and r to the -1, which corresponds to time to the -2 for this frequency squared. We have 1 unit of mass. We have a length squared divided by a length, so that gives us a dimension of length overall. So this is what we've written down on this side of the equation, something with units of per second, kilograms length, meters, and we want it to be dimensionless, so we want to put in some factors of G and C. So, reminder, dimensions of G are per kilogram, so mass to the -1, length cubed, and then time to the -2, and C, our other constant that we want to put in there, is going to be something like length per unit time, because it's a speed. Okay, so if we have some power of these, so G to the alpha and C to the beta, we want that to work out so that when we multiply this by this, we get something dimensionless. So we want this to work out to be t squared, to cancel out t to the -2, m to the -1, to cancel out this dimensions of mass, and length to the -1 to cancel out this length here. We put these terms in here, we can see that G to the alpha, C to the beta would give us mass to the -alpha, because we only get mass from the G term, that's a -1 times alpha, minus alpha. Going to have then length 3 alpha plus whatever beta is, length 3 alpha plus beta, and then time -2 times alpha, and then minus beta. That's this side. If we have some powers of G and C, we want this to equal P squared M minus 1 L minus 1. Okay, and then we can take a look at these and read things off. So we have m to the minus 1 here and m to the minus alpha here, which implies that alpha equals 1. Okay, we have alpha equals 1, and then looking at L, we have 3 alpha plus beta equals minus 1. So 3 alpha plus beta equals minus 1. Alpha equals 1, that's 3 plus beta equals minus 1, implies that beta equals minus 4. And then we have 2 alpha minus beta for the power on time equals 2, hopefully. And if we check minus 2, that's going to be times 1 minus 2 minus 4. So minus 2 plus 4 equals 2. So that does work out. So little dimensional analysis on this problem worked out. We want HR strain to be dimensionless. We know we have a form because we have proportionality to the mass quadrupole time derivative and inversely proportional to distance. Gives us a form like this. It's a relativistic problem, so we know we can have factors of C. It's a gravitational problem, so we know we have factors of G. Getting the units to match up implies that we're going to have a gravitational wave strain that's something like, of course, there could be some numerical factors that we are missing, G over C to the 4 of F squared M R squared over R. Okay, so here's our form. Remember, we're saying that we want to have a large H, so we want something massive. And then we want something where we balance the F squared and the R squared here. That generally smaller things have higher frequencies, so we want to get the trade-off here. So let's take a look at this relationship a little bit more with our next piece of paper. Okay, now if we have something of a physical size R, okay, due to causality, right, R needs to be smaller than the distance we could travel at the speed of light in a characteristic timescale, which is 1 over F. So 1 over F gives us the characteristic timescale at which things change. Multiply that by C. That's as far as you could information could travel in that time. That needs to be greater than the physical size of the object. Otherwise, we're going to have different parts of the object not being causally connected anything. Okay, sorry, question in the chat. Why do we take this first line? Okay, this is something you need to know, that gravitational waves come from the variation of the mass quadrupole moment, second derivative. This is something which you can work out from the Einstein equations, the linearized equations to work it out. Intuitively, if you know a little bit about electromagnetism, you can also get an idea of why this must be, because you know that the source of your electromagnetic wave depends on your variation of your charge. Now, in gravitational waves, we're obviously talking about gravity, we're talking about mass somewhere. So things are slightly different because we can't have the dipole moment. We can't have the equivalence of a positive and a negative charge moving away from each other. We have no negative masses. So we can only have positive masses moving. So we have a quadrupole moment because we need to go up 1 from the dipole. Okay, so that's a very good question. Please do ask these type of questions. Why doesn't it depend on the first derivative of things here? Well, it's second derivative because we need to get the variation, the acceleration of these. If you just have things going smoothly, you get no acceleration. You can just get a propagating solution that you can have. You really need the acceleration. If things are just uniform motion, then you're not getting the distortion, the time propagating materials it's very much just like you have some uniform motion, which is not going to cause this type of disturbances. There's some nice things you can do if you want to delve into this a bit more to work out how this is related to conservation of momentum. The fact that since momentum is conserved, in general, you can't have gravitational waves from the first order case. This is just works out to this. There's some nice examples, in particular in Rindler's book as a first introduction to relativity, if you want to work through that. There's also a similar derivation in book General Relativity by Estacio, Hobson, and Lazenby, which has a good introduction in their chapter on the linearized gravitational waves, if you want to take a look at that. It's not necessarily something obvious, so these are very good questions. For now, hopefully you'll believe me that this depends on the second derivative of the mass quadrupole. Yeah, I'll put some book suggestions in the slides at the end, and you can take a look from that. Okay, where were we? Yes, so if you'll believe me on this, hopefully you'll believe me on this as well, that this you can get from a similar conservation of energy, that it needs to go inversely with distance. Go through, we get this functional form modulo some perhaps numerical factors and some factors on the exact geometry of the source that we've got going on. And this tells us strength of gravitational waves. We want this to be as large as possible to make it as detectable as possible. We have an argument that on the physical size is inversely proportional to the frequency, just from causality, that we want things to be linked. And if we substitute this in to here, we'll find that H needs to be smaller than Gm over C squared over R. Okay, just substituting in this R needs to be smaller than frequency squared, hence you have both squared, so you get this proportionality out. And this is quite a nice relationship, because this here, Gm over R, is basically the form of the gravitational wave, the gravitational potential. C squared here just fixes up the units. And what this tells us from the limit on size is that H here, our time varying gravitational field, the gravitational wave, is smaller than the static gravitational field. So in general, that's a sensible thing to have going on. And we can see that the larger the gravitational potential, generally the larger the gravitational source we can have. So we want things with high gravitational potentials. We want things that are compact. Hence, black holes, we know, are very compact. Neutron stars, very compact. These seem like good sources for us. But let's take things a little bit further. Let's go, okay, let's assume now we have, we need these moving around. Right? They need to be moving around because we have this derivative. So we need to have some source of acceleration. We could perturb the black hole or the neutron star, have its mass distribution moving around somewhere. That is indeed a source of gravitational waves. The supernova explosions you would have heard about in the previous course. One example of this, if you have, say, a rotating neutron star, which is not perfectly symmetric, you'll also have some mass moving around. These are all good sources of gravitational waves, but they're sources that we have not detected yet. So hopefully empirically, you will be able to convince yourself that maybe these aren't the strongest sources of gravitational waves, because those are the ones we're going to detect. So now let's think about another circumstance in which we could have these compact objects moving around. And that would be if we have a couple of them in a binary orbiting each other. Okay, and this is really nice because you have now the masses, total mass will be set by the mass of the binary. They can get really close to each other. The distance they can get to is roughly the same as their physical size because they're very compact. Okay, so R can be small, which is bad, but that means the frequency will be high, which will be good. So let's take a look at this balancing act that we have. So just going on something approximate and using Kepler's laws. Kepler's laws, maybe not the best thing for a relativistic problem.
Hi, Christopher, sorry, we dropped out for a few minutes.
Oh, sorry. What was the last thing you heard me go over?
That time derivative. of the gravitational potential.
Okay, so it's
GM by R is the gravitational potential, etc.
yeah. So we have the time varying gravitational potential, H, our gravitational wave, is being smaller than the static potential here. So GM over R would be what's familiar as a gravitational potential. Units of c squared give us the right dimensions, and if you know a bit of relativity, you'll recognize this as part of the time part of your gravitational potential for something like the Schwarzschild, something like the point mass solution. You'll see this come up. So we have the idea that our gravitational wave signal, our H, is smaller than the static potential. That makes sense if you, in the idea that a gravitational wave is some type of perturbation to the gravitational field that changes. We're all happy with that. And this also sets the characteristic scale at which we're talking about things that we want. Larger gravitational potentials, and that will hopefully give us larger gravitational waves. So we want massive things, ideally close by, but we can't change that with such massive things. So things like black holes or neutron stars would be very good sources here because they're very massive. We know they're very compact. So isolated black holes or neutron stars, if we can perturb their masses so they accelerate in some way, could be a source of these type of masses. So actually talking about supernova explosions, which you covered in the last part of this summer school, that's a very good gravitational wave source because you have masses comparable to the stellar mass being accelerated. So quite high frequencies associated with this motion. That's good. We could have rotating neutron stars.
Question.
Please.
The small r at the bottom in H less than GM over C square R, yes, that. Is that the distance to the source, or is this a typical distance of the binary or the separation?
Yeah, this is the distance to the source. So how far away we are from the source. So from Earth to the source is the common way we do this.
Okay, all right, thanks.
So the potential we would feel from the source is safe. And this is a good question. We'll come back to this in just a second to look at this in a moment. Okay. But yeah, coming back, we want, say, rotating neutron stars could be a source. We have massive objects moving quite quickly, but we've not seen gravitational waves from supernova explosions or from rotating neutron stars yet. So hopefully you can take empirically that these are maybe not the strongest source of gravitational waves. Another time we could have these massive objects moving around, so having some acceleration, is if they were in a binary, so orbiting each other. And this is quite nice because now we have potentially doubled our mass because we have two of these objects, making m bigger. We like that. And these can get quite close to each other. That will, of course, reduce R, but increase F. Okay, so that we have our balancing act coming back in, whether making this a good gravitational wave source. So potentially they can get within their physical size of each other before merging. So let's take a second to look at this orbital motion a bit. So we're going to have a go with Kepler's laws. This works out surprisingly well in the relativistic case. But remember, we're just doing some approximate astrophysics at the moment. So hopefully you'll be happy even if it's not exactly what we want. From Kepler's laws, our orbital frequency is something like Gm over R cubed, here M being our total mass, R being this here being the characteristic size of our object, the R here. This would be the interbinary separation. So this is, well, the radius here. So that's something like big R in this scale here. Okay, so this is our orbital frequency. As you see, it depends on the orbital separation. Let's substitute in a characteristic scale for something that's very close together to see how that works out. Now, a characteristic scale in relativistic problems is the gravitational radius, which we can again just get on dimensional grounds of Gm over c squared. Okay. If you're familiar with, say, the Schwarzschild metric or the Kerr metric, you know that terms like this come up quite a lot. The Schwarzschild radius, the characteristic radial measure, so more circumferential measures, is twice this often use this as the characteristic size of the event horizon, and Kerr black holes. That's a Schwarzschild solutions for non-rotating black holes. Kerr black holes described by something which, again, looks very similar to this. So let's work in terms of this gravitational radius, and let's just take something which is not quite this scale, but a bit bigger. So let's say we're 10 times the gravitational wave, sorry, the gravitational radius as our characteristic size for our binary. Substitute this in to our orbital separation. Is our orbital frequency 1 over 2 pi squared. Have GM, going to have our cubed on the bottom. So this is going to be 10 cubed, and then our G cubed here is going to be C squared GM all cubed. F orb is going to be something like 1 over 2 pi squared, 10 cubed. Okay, and we can change this now to C cubed over GM all squared. Okay, and this here going to be something like 2 pi squared, also it's going to be, yeah, what's that going to be? Approximate value, so pi squared, that's roughly 10, so 10 to the 4 times 4, 4 times 10 to the 4, okay, as our numerical constant, so it's going to be something like 4 times 10 to the 4, C cubed, GM squared, and so our orbital frequency is going to be something like 1 over 200 C cubed G over M. Just very roughly what we've got going on. Okay, now let's take a specific example, just see what sort of numbers this works out for. We know we want something massive, so we're going to have something roughly on the order of a stellar mass. So let's take M equals 1 solar mass. Okay, and if you substitute in these numbers, you'll find that the orbital frequency will work out to be something like 1 over 200 times 200 kilohertz. So roughly 1 kilohertz. If you substitute in one solar mass. Okay, so orbital frequency about 1 kilohertz. That's pretty high. That's good. This is coincidentally, one could argue, the frequency range that's roughly equivalent to advanced LIGO, advanced Virgo, or CAGRA. If you know your gravitational wave sensitivity curves, they're often something bucket-like here. For our ground-based detectors, this LVK type thing. This function of frequency, this is our noise curve. This peak here is of order 100 hertz, so a few hundred hertz is the bucket here. Kilohertz is a little bit up here. So the gravitational wave detectors were designed with this type of scale in mind, which is why it works out, but it's also quite nice to mention. Anyway, our orbital frequency, roughly at kilohertz. Oops, sorry, just for clarification. Yes. Okay, excellent question. I've just glossed over something here. Thank you for pulling me up on this. So yes, this is our orbital frequency. So this is the frequency at which our binary goes around. Now, I've implicitly assumed that this is related to our gravitational wave frequency. We are only doing some approximate physics, some twiddles here, so factors of 2 and so on, not too important. There is a relationship for a circular binary, which is the gravitational wave frequency is equal to twice the orbital frequency. This comes basically from the quadrupole moment again, that you have a peak each time one of these two objects comes by you, so you get 1 peak per binary, so that works out to be a factor of 2 So yeah, roughly 1 kilohertz for the gravitational frequency, 2 kilohertz for the gravitational wave frequency for 1 solar mass binary here. But yeah, factors of 2, somewhat below our characteristic scale for accuracy in these approximate things. But yeah, it's a good question. Okay, why were we doing this? Well, we now have an idea of where we want to build our detectors, but we also can now go back to our gravitational wave stream because we want to have a look at our characteristic size and just check if our binary is a good source of gravitational waves. So let's take a look again at our equation for gravitational wave stream here and substitute in our characteristic frequency that we've got. So we've got h something like g over c to the 4, then frequency squared, which is going to be something like gm over r squared, so r cubed, m r squared over r. Okay, I've lost the factors of 2 pi because this is our very approximate twiddly physics, and we don't know if there are some other geometric factors of 2 pi and so on, but it's just something like this. Okay, now this is important because we've previously said that generally as r gets bigger, f gets smaller. We know there's an inverse proportionality of between these, so we don't know which wins, whether it's better to have a bigger source that varies over longer timescales or a smaller source that varies over shorter timescales. And we see after substituting in here, we have an r cubed on the bottom and an r squared over the top. So for a binary source, we're going to have something where smaller r wins. We're going to have something, we can collect together these terms. Have 2 g's, g there, have an m there, so gm squared. Can have a c squared or squared, that gives us c to the 4. And then we're going to have 1 over big R, that's our binary separation, 1 over little r, that's our distance from our binary. Something like this. Okay, so smaller sources, stronger gravitational waves. This is good because we can, if we go back, we have a very tight binary. That will be very small. That should give us strong gravitational waves. We want something massive. We want something small. Ties into our intuition for stronger gravitational fields. So things like black holes and neutron stars, which are very compact, going to be the best gravitational wave sources because we can have a large m and a small r. Okay. Now, this term here is also something we've just met. It's our characteristic gravitational radius. So we see that this here works out to be something like rg squared over r. Too many r's perhaps. But this then works out that we've got the right dimensions. This makes sense. If you go back to our guesstimate of what a characteristic type binary might be of 10 rg, we can then substitute this in to be rg over 10 times the distance. Something like this we might guesstimate as our top gravitational wave strain. Now, if we were to put in some just toy numbers again, see what type of scales we're looking at. So we'll go back to our m equals 1 solar mass. And let's pick r equals 10 to the 24 meters, that's about 30 megaparsec, characteristic scale for local galaxies. You'll find that if you substitute in to here, you'll get something which is roughly 1.5 times 10 to the 3 for the gravitational radius, and that 10 times r is going to be roughly 10 times 10 to the 24, which works out to be roughly 10 to the minus 22. Okay, so this is the type of scale we're talking about for something of a sensible astronomical mass and something on a sensible gravitational astrophysical distance. I've picked these numbers somewhat arbitrarily. We could have something in our galaxy that would just be a few kiloparsec. So that would be, a factor of 1,000 larger, but that would be potentially quite rare. If we're talking about our first gravitational wave detections, they were a factor of 10 further away. So, you know, this would be a factor 10 smaller, something like 10 to the minus 21. Okay, so we know that we have, when we're designing our gravitational wave detectors, we want something round about the kilohertz range, and we want to get something down to a gravitational wave strain of 10 to the minus 21, 10 to the minus 22 for the magnitude of our bucket. Noise curves often listen to SN, which is something like the square of that. But we have the idea that we have very sensitive detectors. Okay, but these are about the best sources we can have because of these distances here. The fact that we can actually detect them at such large distances is really quite remarkable. If we were talking about the rotating neutron stars or supernova explosions, we need to be much closer to work out the same gravitational wave strain, just because we don't have the same amplitude at the start. Now, a couple of things I just want to point out about this magnitude, well, three things, in fact. Canonically, people often talk about 10 to the minus 21 as the gravitational wave magnitude. 10 to the minus 21, roughly 10 to the minus 21 as our characteristic scale. If you're doing some calculations and you get a gravitational wave amplitude about this size, it's generally a good thing. Means you've got a good sanity check going on. I picked numbers somewhat arbitrarily for my calculation here. So it worked out about right, that's good. If you're simulating some waveforms for binaries at a sensible distance and want to check that you're not squaring them or anything like that, 10 to the minus 21 is a good thing to look for. It's also a great number if you're ever giving a public talk and you want to impress people with how sensitive gravitational wave detectors need to be in order to measure this, as 10 to the minus 21 as a strain works out exactly like order of magnitude for the distance between the Earth and the Sun to the diameter of one hydrogen atom, or the distance from here to Alpha Centauri, our near neighboring star system, to the width of a human hair. Okay, so it's a great scale for putting in public talks to get an idea of the scale here. But two extra things to watch out for here. If you ever doing some calculations and you work out that you've got h of 10 to the minus 34, that probably means you're accidentally doing a problem in quantum physics and have used Planck's constant instead of the gravitational wave strain. The second thing to note is that h, it depends on our distance to the source. People always, well, not always, but often write that gravitational waves are very weak effect. We know that they are a perturbation to space-time. We know that they're smaller than the gravitational potential, what we went through here. So gravitational waves are small, but it's only 10 to the minus 21 small because we're at an astrophysical distance to them. If we were really close to the source, we could have a much larger h. So it would always be less than 1, as it will work out, but we could have h of just a few percent or 1,000% if we were really close. So it's not always the case that gravitational waves have to be small. It's just small whenever we're talking about astrophysical sources. What's the minimum, okay, question here, what's the minimum detectable strain? Now, this is an excellent question, and it's one that I can't give an exact example answer to. And because the reason why you can't say immediately what the minimum detectable strain is because it depends on a couple of things. So one is if we go back to our noise curve, we'll talk about this a bit more in the third lecture. The noise curve, hopefully you've seen some plots like this, which have a power spectral density, often written as SN, or maybe the square root of this, as a function of frequency. What this is really showing is the variance of the noise. That in our detector, we're measuring a strain, so as a function of time. Okay. We have some output from our detectors, which will be a stretching or squeezing, so we'll have some time series of something. H. Okay, now this will be a zero mean process. On average, the gravitational wave strain is 0. Just sort of by definition that we're looking for changes, so it's always a 0, no changes as the relative amount. Now, because we have many sources of noise in our detector, this can be from the photons arriving discretely, giving us some shot noise. It can be emitting some pressure on the mirrors. That gives us some radiation pressure noise. It could be seismic noise from the rumbling of the ground, which is important at low frequencies for our ground-based detectors. It can be the thermal vibrations of atoms in the mirrors and things like that. We have many sources of noise, and so we characterize this by a variance which gives us this different frequencies, our noise curve. So in theory, if our signal is bigger than our noise, we would be able to see it. There are two complications to this. So one is that our noise is not a perfect Gaussian process, so something that just has a characteristic scale that it varies over, and we know the statistical properties very well. It also has some non-Gaussian features. It has some extra bursts of noise over various timescales. We'll talk about this a bit later on in a specific example of glitches, which are short bursts of noise. And so because we don't know, if we see something in our data which is a bit louder than usual, okay, we don't necessarily know whether this is a glitch, a burst of noise, or a real signal. Okay, so we need to empirically determine the noise properties. And so it's this empirical noise properties that sets when you can distinguish a signal from the noise. And this particular threshold of when you can do this depends on the algorithm you're using, the search technique you're using, and the properties of the source. So the signal, this particular signal you're looking for, determines when you can make things detectable. So there's no one minimum detectable strain, because it depends on the form of the signal, the current performance of the detector. So you can roughly guesstimate it as being similar to your power spectral density, or rather the square root of that, the amplitude spectral density, but it does depend on the signal. Excellent question, and yet we'll come back to this in lecture 3, and then hopefully it will make a lot more sense filling in some of these pieces. Okay, we've done a lot of different things, putting them together. We started from an idea of where gravitational waves come from, some masses wobbling around. We know it varies with the amplitude. We got a rough functional form. We know it depends on the size of the object and the characteristic frequency of it, and the mass. So we want heavy things moving around as quickly as possible. We know there are some physical limits on the size of these objects. There's typically an inverse relationship between the physical size and the frequency, which is a balancing act. When we have a binary, though, this balancing act wins in favor of having a higher frequency. So having a higher frequency produces a larger signal. So we want compact objects, so things which are physically small, so they get close together, things with a high mass. So we want compact objects, black holes, neutron stars in binaries, and these make really good gravitational wave sources. But this is why we're really interested in these sources for our gravitational wave astronomy, because they are good sources. So given that we can see them, we're then interested in what we can do with these measurements, and this is where we come into the astrophysics of them. Okay, now, as I said, there's some approximations in this, but there are many things that we can model. So let's take a quick break from this paperwork for now and come back to think of the question. So, okay, we know that these are a good source to look for. What can we actually see and what can we learn from them? So let's go on and talk a little bit about how do we form these binaries and what do we do with them. Now, the good news is that we know what these signals should look like. And here we go. Here's a nice video, one of my favorites, of a numerical relativity simulation of two black holes merging. Okay, so here's a visualization of the space-time in the colored here. Redder colors mean highest curvatures. You can see the black holes orbiting around each other. As they orbit, they emit gravitational waves. You can see the ripples in the background, which represent these. These carry away energy and angular momentum. As the binary loses energy and angular momentum, it shrinks. So the binary get closer together, the orbital frequency goes up. It emits more gravitational waves. So we have a runaway process. Frequency goes up, they get closer together, and then eventually these two will plunge in and merge, form a bigger black hole, coming in up. And here we go. Simulation slows down for the dramatic point. They merge form each other, they form a single black hole that's perturbed, so it will wobble around this. Here we go, there's the merger. And then we're going to get a ring down as this wobbles around, emits final gravitational waves as it settles down to its final state. Okay, so that's what a simulation looks like. Let's have a look at this again.
Hello. Hi.
Oh, yeah.
I have a question. So
Yeah.
last time when we were doing this order of magnitude calculation, you invoked like this Kepler's law, right? To get that number of 10 to the power minus 21. But now you just said that energy is carried away, energy and angular momentum is carried away by the gravitational waves, meaning it's not a conservative system. And Kepler laws were defined for a conservative system, right? So this is good enough for an order of magnitude estimate, but can we at any point of time while calculating the waveform use something like Kepler's law? Because it's not a conservative system.
Excellent question. Yes. So the answer is yes, that you can. Actually, if you're ignoring black hole spin, it basically works out to be the same functional form of the equation. The difference is that when you come to work it out is what the definition of big R in your equations means. So this binary separation. So in Kepler's law, it is derived in a Newtonian universe. So space and time are absolute quantities, and it's very obvious what R is. It really is just the, your binary separation here, set by the physical size of your, you can measure the distance between them here. In a relativistic system, it gets a bit more complicated what R means, because you have non-Euclidean space-time, you have deformed geometry. And one of the interesting things about this is that if you have a non-Euclidean circle, so here's a circle, in Euclidean space, we know that if we have a radius here, let's call this rho because we've used R too many times, we know that the circumference is 2 pi times rho. In a non-Euclidean space-time, this no longer applies. We can have some other relation here. So when you're talking about a circular orbit, you need to be careful about, do you mean R as some kind of radial measure or some kind of circumferential measure that you're dividing by 2 pi? And by picking the right definition of R, you can get an equation that basically works out to this. You want it to be a circumferential measure rather than a direct radial measure, but it does work out surprisingly to be basically the same functional form. So it can work for this purpose of order of magnitude things. It is good enough. You can define something better. It becomes a bit more ambiguous to be able to do it. But yeah, there are ways of doing it, and it's a good question. And if anyone's ever giving you a talk on relativity and you want to pose a slightly difficult question, it's what actually do your coordinates correspond to? Is your R a measure of radius or circumference? If you remember when I was introducing here our gravitational wave radius, and I said that this came up in the Schwarzschild metric. If you want to look into your black hole spacetimes at some point, you'll figure out that this actually is a circumferential measure. So it's a measure of how far it is. If you go around your black hole, it doesn't correspond to the same sort of distance to the center of the singularity of the spacetime in the same way. Yeah, it's easy to get tripped up on these things and be careful. But we can find some similar things if we are properly interpreting the geometry of our spacetime. Okay, so coming back to this simulation, and this is a good question actually, because some liberties will have been taken in making this animation. So this is a numerical relativity simulation, so the space-time has been solved for exactly, but in order to embed it in a way that we can see it, some artistic license will have been taken. So I'm not sure exactly what choices were made to do this, whether they picked radius or a circumference for distances and things like that. But for our just qualitative understanding, this doesn't matter too much. So energy momentum being carried away, we spoke about, and we said that this will get closer together and eventually merge. And we can simulate this. This is doing numerical relativity. We can also make great progress for different parts of this signal using other approaches. For example, using post-Newtonian theory. This is where we start with Newtonian gravity. and then add in corrections to this based on perturbations of this to add in the relativist effects, add a series of these to higher and higher order to get post-Newtonian effects. This works very well for this in-spiral portion here. We can use perturbation theory to understand the ring down of the final black hole at the end. Can use effective one-body formalism to try and get some extra models of the dynamics in the in-spiral and marry that to the merger as well. So we can get some calculations of what this in-spiral looks like, this merger looks like. That's really numerical, but what the ring down looks like, that's great. But we can calculate what this gravitational wave signal looks like, and we know what this varies in terms of its masses. So since we know the masses, spins, distance, and so on, we can calculate what the gravitational wave signal looks like. And so we can map this to our data. And so working backwards now, we can go from our data to infer what the source masses are. So we can measure the masses of our black hole, its distance to it, from this characteristic pattern of wiggles, which you can see at the bottom of the screen. This is what the gravitational wave signal looks like. So we have a good source, it's detectable, it's a loud signal. We know what it looks like, which means we can look for it in the data, which is very useful for identifying the signal from noise. And then when we found it, we know there's something there, we can infer what the source properties are. So this is great, we can really do astrophysics of these sources, we can figure out the properties of the sources. So we can go from wiggles in our detector to an understanding of the source. So these are a good source, not only for detectability, but for measuring the properties of the sources. So given these properties here, we can now understand something about the progenitor systems. We understand the properties of these sources, so we can compare them to theory to work out what's going on. Okay, so that's what we're going to be talking about in later lectures, is really this process of how we do this data analysis and what the particular physics is of these sources. But now let's take a step back, and these are only interesting sources if they actually exist. Right? We know they should be detectable. We know that we can measure their properties if we were to see the signal, but if there are no signals to see, then obviously this is all irrelevant. So let's take a moment to think about how we could potentially get these systems. Okay, now what this plot here is showing is as a function of the orbital separation. So this is the semi-major axis of a Keplerian orbit. So this is taking just a very Newtonian picture of the in-spiral times. And here's the eccentricity. And these tracks here show how an orbit would evolve as a gravitational wave emission happens. So this is using a particular famous calculation done in the 60s for gravitational wave emission. It assumes Keplerian orbits, so it's not particularly accurate when you get very close to merger, but is good for wide orbits. It's a good first approximation. And it's looking at this, and we, question. Okay, question, why does it emit energy and angular momentum? So we have any accelerating object will emit gravitational waves. These gravitational waves have energy and angular momentum associated with them. Since they're being radiated away, they must come from somewhere, so it's being extracted from the binary orbit. So this is just the gravitational interactions lead to the emission of energy and angular momentum. It's the same way that if you had accelerating charges, they would emit electromagnetic waves. Those would carry away energy, angular momentum, thus dampen down the energy of the system. Here we're losing system because the gravitational waves are carrying away energy and angular momentum. Energy and angular momentum will be carried away whenever you have accelerating masses. The larger the gravitational waves, the more this is being carried away. So this is not noticeable, say, if we're thinking about the Earth orbiting around the Sun, anti-gravitational wave energy and angular momentum loss is negligible. But if we have a strongly relativistic binary, we'll see that this is less negligible. Okay. So this in particular is what this line is showing. So for separate initial conditions, this is showing the time to merge, but in log base 10. Okay, so you'll see that for something at 1 AU, yeah, this is for solar mass objects or so, takes around about 1 billion years to merge. Okay, this is a very long time. So if we talking now about characteristic sizes of things, our solar radius is about 10 to the minus 2 astronomical units. Certainly if we were trying to fit 2 suns in, we couldn't fit them in to less than 10 to the minus 2 astronomical units. So if we had 2 solar masses in this less space, and that we'd have stars that would merge. That's no longer a binary source, it's just a big blob of mass. So that's not going to be a gravitational wave source. And we can see that takes 10 to the 5, so still quite a long time to merge. If we had 2 suns next to each other. If we were talking about larger stars, those have larger radii. And if we're thinking that these stars not only need to go through their main sequence, but their later evolution as red giant stars, blue giant stars, whatever you have, later stage of evolution, these stars puff up. They can puff up, they can easily be 1,000 solar radii. So that puts us out at 10 astronomical units to avoid these stars merging. Okay. So we'd be all the way up here if we want stars that don't merge to each other, that will then eventually live their lives as binary and collapse down to black holes. So we're somewhere up over 1 billion years for these things, for them to merge. Okay, question here, energy. Now that's an interesting question. The energy and orbital momentum are, do they depend on the final gravitational waves and not the earlier stages? Yeah, there is, when we see our gravitational wave signal, we're only seeing the properties of the source at the current time, modulo the time taken for the gravitational waves to emit us. But the orbit should decay in a deterministic way. So you should be able to map back, given that you have this conditions now, if it only was evolving due to gravitational wave emission, this is what it should have looked like earlier. So we can map back, if we could perfectly measure the eccentricity and orbital separation, we should be able to map backwards to get these. In practice, we will see, again, from this side here, eccentricity gets damped very quickly. So we get this drop off, it go down to eccentricities of 0 relatively quickly compared to the changes in the solar major axis. So orbits circularize very efficiently due to gravitational wave emission. This means in practice, we don't expect to see eccentricity in our binaries when we actually see them close to merger with LIGO and Virgo. And since it's very close to 0, it's very hard to measure. So it's very difficult to infer earlier eccentricities because it's so small. Maybe not impossible, but certainly very hard. So we will often approximate things as being perfectly circular for various reasons. Coming back to this point here, so we have some idea that if we want 2 stars as close as they can be without merging, they're going to take over 1 billion years in order to inspiral due to gravitational wave emission. Right, this is a problem because our universe is only 14 billion years old or so, so just 1 order of magnitude up, exactly in the range that we're talking about, if we can get the stars as close as possible before merging. So to actually produce gravitational wave sources that we can see via this channel that we think is promising from binaries, we need some mechanism that will bring stars closer together. So we have this idea that at some point in their evolution, they're very big and puffy, but when they collapse down to black holes and neutron stars, they're very small. So we really want some mechanism that can take a wide binary, 2 stars far apart from each other, and then bring their remains, the black holes and neutron stars that they leave behind, closer together later in their evolution. In that way, we can start off somewhere where the gravitational wave timescale is very long, but we bring them close enough to merge that there's a reasonable reasonable delay time, 1 billion years, less than that, for them to merge. So we could actually hope to see some in our detectors. So a lot of the problem in source modeling was figuring out how this is possible. And now that we have observed gravitational waves, we know that it is possible, that there must be mechanisms that take stars initially separated by quite a distance and bring them closer together. That's what we're going to spend a bit of time talking about over the course of some of the next lecture and the remainder of this lecture are the different ways we can get black holes basically close to each other. Okay, so just taking a second, does that make sense? That stars are quite big, so they're very far apart, so they would take a long time to merge. We want things close together so they merge in a shorter time scale. So we need some way of taking the remains of black holes, remains of the stars, the black holes on each stars, bringing them closer together so that we can get things merging in a short enough time scale that we can actually hope to see a large number of them. People happy with that basic idea? You're always allowed to be unhappy, I should add, and we will try and fix that. Okay, I have one yes. That's good. I guess a few of you are taking a moment to think about this. The tutorials associated with this course should be well designed, and you will do some calculations to work out in-spiral timescales and the characteristic size of stars in order to as part of this. So this will hopefully prove itself. And yes, this figure is for assuming equal masses, if I remember correctly. So you can get some variation here based on the mass ratio and the total masses in the system. This dark blue line is showing all the points that could merge for, I think, a 30 plus 30 solar mass binary within the age of the universe. So if you want to try and trace that out. Anything on this side won't take too long. This, by the way, is a very nice paper on the formation, what we understood of the formation mechanism for these binaries at the time of our first detection. So at the time, this was the last time when these were all predictions and not some post-dictions, having seen some. And I think I interrupted someone asking a question.
What is the green line towards the left-hand side?
Yeah, so these are different masses assumed for these things. So actually, we take a look at this binary, let's see if this works. Okay, let's look at this paper and have a look at its abstract. Can you still see my screen? Okay. What was the number? 03845. Oh no, I've got that wrong. Calibration one off, I think 6. Yeah, there we go. Okay. And here's the figure. Okay, semi-major axis A, and eccentricity in order to merge within 10 gigayears, right? So roughly the age of the universe, is this thick blue line for a binary black hole with 15 and 914 masses, so 30 plus 30, roughly same masses. Thin solid lines with circles represent the evolutionary stages of example systems, so how long it takes from these different lines. The dashed lines are, separations of 10, 20, and 40 solar radii. Okay, a green dotted line shows the trajectory of a binary that has 0.1 eccentricity at gravitational wave frequency of 10 hertz. Yeah, so that's the different one. So this one would still have some eccentricity left that would be detectable in our observations. So you can see you need to start at really high eccentricity comparatively at a given radius in order to maintain any residual eccentricity that would be measurable in the LIGO-Virgo-Kepler band. Okay, good question. If anyone does have any questions about the figures or ideas, please do speak up. And I was hoping we would do exactly this type of thing of, look at actual papers and go through things to give you more of an idea of what exactly is going on.
Hi, I have one very small doubt. So when we talk about different eccentricity, do we mean that there's a one-to-one correspondence to the formation channel? Like these eccentricities would be in some formation channel and not the other?
Excellent question here. Yes, so some channels would be expected to lead to eccentricity, while others would not. So this is exactly what I was hoping to go on to next, actually, is talking about the different channels and what things to look for. So we've spoken about the fact that we can measure masses, we can measure spins, can also measure distance from the amplitude of the gravitational wave signal. So from these, we can infer something about the sources. So this is what we're going to be using these measurements to look at the source properties. Eccentricity is another one that potentially is a good proxy for these different formation channels. So we want to use these together. And as we go through, we're going to see that different channels make different predictions for these. And this is one of the ingredients that goes into doing these population inferences, is adding together the number of sources you see with different properties to infer what's going on astrophysically. So excellent question. Shall we take a moment now, go back to think about how are we going to get our merging systems? Okay, we know that we want to end up with, say, two black holes very close together. But if they started out as a binary, they would have been, huge stars, so many thousands of times this size at some point in their evolution. So they would have merged, can't fit two stars into this region. So we need to get some mechanism to start off with stars far apart and then migrate the black holes together. So I don't know. So I know we have people from a mixture of backgrounds. So does anyone know the typical types of channels or any of these that have been suggested in order to get merging black holes? Okay, it's okay if you don't know. That's what we're going to talk about here. But I was just wondering if some people will have come across a few of these.
I don't completely remember all of them, but they're like hierarchical mergers, then they're like binaries in galaxy clusters and sort of channels, right?
Okay, so yeah, a couple of ideas going on. So that hierarchical mergers, that's a bit more complicated, but let's go through and talk about a few of these different mechanisms. So we have already an idea brought up here of, say, in galaxy, in various clusters. So one way to get around this problem, that we know we can't have the stars being close enough together, is imagine, well, why do we need the stars to be in a binary in the first place? All we need is for their remnants to end up in a binary. What if we were somewhere like a globular cluster? Okay, globular clusters are, old clusters of stars. You have many stars in a tight area. Similarly, you could have a nuclear star cluster. Which is a similar large cluster of stars in the center of the galaxy. They're bound gravitationally. And the idea here is that we don't need to have two stars in a binary. All we need is enough black holes in a small enough region that as these move around on their various orbits, every so often a couple will get close enough together, so that they will get close enough together to form a gravitationally bound system. So they will form a binary after completing all that evolution. So we don't need them to start off in as two stars. They can just form later in life. So doing so is quite improbable. Getting two black holes close enough together to that they form a bound binary is improbable. So you need many stars in a dense area. So more stars there are, the more interactions there are, the more the probability is that two will get close enough to form a bound pair. And the denser it is, the more interactions you have, and also the smaller the characteristic scales. So we have two binaries getting close together, they form a binary. And what is nice about the way that gravitational wave interactions happen, that once you have a binary formed, so you have two objects orbiting each other, if then another object comes past it, okay, that will have an interaction here. And this tends to harden the binary if it is already quite tight. So by harden, I mean extract energy and angular momentum, so the orbit shrinks. Okay, so you have lots of interactions going on, potentially. Each one of those hardens the binary slightly. And so you have a way of shrinking your orbit, driving it smaller and smaller over time. So you hit the regime where you get gravitational wave emission taking over and getting an in-spiral in a close time. So these formation channels are known as dynamical. Okay, because they depend on the dynamics of the system, the gravitational wave interactions driving them together. We can also have perhaps a few binaries formed in these clusters, or nuclear star cluster. They can be quite wide, so wide enough that they can fit all the stars in. And then through these interactions, they can harden up and shrink the orbit later. So this puts us into the gravitational wave. Okay, now a question here. I said these interactions tend to harden the binary. That's not always the case. Sometimes you will indeed have a three-body interaction going in. So you start off with your two black holes orbiting in a binary. You're going to put in another object. Let's make this red. This is going to come in. Okay, and then we're going to have some complicated interactions. The red one's going to steal the partner. They're going to form a new binary. And then the other one's going to get ejected out. Okay, going to get swapped. That does happen. That's quite common. What tends to happen in this case is that you end up with a binary that's made up of the more massive objects involved. So if this black hole was more massive than one of the other components, it's more likely to stay behind in the binary afterwards. And then this is again good for our gravitational wave emission, because if you remember our gravitational wave, we emit more gravitational waves when we're more massive. So we have louder signals and also shorter in-spiral times when we're more massive. So these type of dynamical interactions favor the more massive binaries, which is exactly what we want for gravitational wave sources. So excellent question here. And this is an important mechanism in these dynamical channels, that we have binaries forming either dynamically or maybe forming from two stars that were wide apart. They get hardened by some interactions. You maybe get exchange of partners via other interactions. And the end result is you will end up with bound binaries quite close together, often with high mass components. Okay, there are a couple channels here. So globular clusters, big balls of stars, nuclear star clusters in the center of galaxies. There's an extra step that happens in the center of galaxies, which can also be important. Let me just check the time. Yeah, okay. So I don't know how much you know about the centers of galaxies, but often there is a supermassive black hole. Oh, sorry, my question. Hardening of a binary, that means getting tighter. So your orbit shrinking, extracting energy from an orbit. So the objects get close together. That's the term you'll see in the literature is hardening. From our gravitational wave point of view, hardening is good. That reduces the in-spiral time and makes us more likely to see a merger, which is what we want. Okay, going back to the center of galaxies. The center of galaxies tend to have a supermassive black hole, million solar masses, maybe a billion solar masses. We have our stars orbiting around it in our cluster. Okay, you can also have a disk of material, okay, orbiting around your supermassive black hole, and this is what leads to active galactic nuclei, AGN. And often people here talk about active galactic nuclei. You have some disk of material, it gets secreted out, launches jets of material, which we can then observe as, say, quasars, radio galaxies, and things like this. Okay, now, this is important as an extra way of forming gravitational waves sources, as if we have this disk of material, we can potentially have objects embedded in this disk. Okay, and due to viscous drag, they can be sort of sucked into particular positions together, and you can have accretion onto the binary. Okay, and you can even have stars forming potentially in these disks at large distances, depending on how big it is. But you can have binaries then embedded in this disk being pulled together and formed and tightened up due to accretion, that they absorb material, they get more massive. So as well as the nuclear star clusters having dynamically formed binaries, we can also have binaries in our disk forming. Now, if we come back to this idea of things we can measure, okay, we have the masses of our black holes. Okay, we know that the masses of the black hole will come from the masses of the stars, but we can see there are potentially changes to these masses, that dynamical interactions will favor larger masses. Potentially we can grow black holes to larger masses as well due to accretion in the disk. Okay, so these will impact measurable effects. Coming back to eccentricity, that if we have a binary just forming, it could be very eccentric. Okay, so eccentricity would be an indication of recently formed by a dynamical interaction. It might be that we've just undergone a close encounter with a third companion that has excited some eccentricity, particularly in fact if we have a third component orbiting around our tight binary, that can exchange angular momentum from this orbit to this orbit and drive some eccentricity. Okay, if we were embedded in a disk, the accretion should dampen down accretion and make us more circular. If we undergo lots of small interactions, that should make us more circular. If we're thinking about the spins of black holes, okay, black holes have a mass and a spin. The spin has an orientation. For dynamically formed binaries, we're just throwing together two black holes, so the spins should be isotropically distributed. We have no preferred orientation. They're just going to be randomly associated with each other. If they're embedded in a disk, potentially we can have accretion onto the black holes that spins them up. So we have our black holes in our disk, they spin up, and so we expect them to be spinning around in the same way as the sense of the big disk of material is going around. So we have two black holes orbiting each other with aligned spins, we would expect in this case. Okay, so dynamical formation, random spins, AGN disk, aligned spins. One one big channel left to talk about, which is known as isolated evolution. And this is the idea that we really do have two stars that live their lives together as a binary. So they formed potentially in a galactic field. Most stars are higher multiples. So we start off with two stars. We know that they're going to be too far apart from each other to merge in most cases. So we need to think of a way to bring them close together. So there are a number of ways of doing this. The first, which we'll go over as perhaps the rarest, is if they're very close to form stars together, they will get tidally locked as they rotate around each other. You get tides raised on the stars, so the stars will rotate at the same rate as they orbit each other. So if they're very close, they will be rotating very quickly. And what is nice about this is that stars, if you think about a star, it normally has a core, okay, where all the nuclear burning is going on, okay, and then you have elements being formed in shells around it. So you might be As you get older, you'll have burnt all the hydrogen in your core. You'll be now burning helium, but you'll have hydrogen in the core about it here, and then eventually you might have burnt all the helium in the core, and you'll start burning carbon, and you'll get shells of material going up. It's during these evolutionary phases where you have chemical composition changes that your star will start to puff up, that you get your red giant star, you'll get the big expansion. And this is where we know you get stars overlapping with each other and merging. However, if you're rotating very quickly, you mix all the different layers of your star, so it stays chemically homogeneous. Okay, if you're chemically homogeneous, you then don't go through the same stages of puffing up. Okay, so you stay small, and so you can start off close together. You won't merge due to the stars expanding, and as they collapse down to black holes, they will be close to each other, and they should be rapidly spinning. They should be rapidly spinning because the stars they formed from were rapidly spinning. So in this case, we would again expect stars quite close together. They need to be quite massive to go through this process, and they should have aligned spins. Okay, so that's the first way of isolated evolution, of going through this. Now we're almost out of time for this lecture, so I propose we're going to stop here for now, and we'll pick up next time going through other details of isolated evolution and how we can get stars coming close together to merge. And we'll go through various types of mass transfer, so where mass is transferred from one star to another as they change inside. Okay, repeat the last point. So I think this is on chemically homogeneous evolution. This is the idea that if you stars expand when they go through the later stages of evolution, where you start having a distinction between the chemical composition of your core and the outer envelope. Okay, if you have lots of rotation, which can happen if your stars are very close, so they become tidally locked, so they raise tides on each other, which induces rotation. The rotation rate is basically the rotation frequency is the same as the orbital frequency, which because they are close together is very high. In this cases, you get mixing inside your star, or the different layers get mixed together, so you're chemically homogeneous. The chemical composition is homogeneous, which means the same throughout. Approximately the same throughout, it's not exactly the same. In this case, because you don't have the distinction between core and envelope, you don't have the expansion. So your stars remain small. Because they remain small, they never puff up and overlap and merge as stars into one just big star. They remain two separate stars, and so they can collapse down to two black holes, say, which are close enough to merge in the gravitational wave timescale. So we get over the problem of them being very big stars not fitting in orbits that will merge within the age of the universe. Coming out from this, you'd expect two black holes which are merging with aligned spins, because the two stars they were forming would both be spinning in the same direction, aligned with the orbital plane. Okay, so we've gone over a couple of dynamical interactions. We're starting on isolated evolution. Next time we'll come back to this and talk a bit more about this physics here. Okay, thanks everyone. That's a long talk. Do we have, yeah, if you have some more questions, you can ask them now. You can also drop them into Slack, and of course bring them along to the next lecture, and we'll go through there. And if there are particular topics that you're very interested in, yeah, please also drop that in as we go through the course, so I can try and make sure to spend enough time on those topics for you. Okay.
Hello. So I have a small doubt. So somewhere you wrote that this frequency of gravitational wave is 2 times the Keplerian frequency of this binary system. Is there any reason why it should be so?
Yeah, so it's twice if we have a circular binary. If we have an eccentric binary, we have a range of different frequencies going on. The reason it's twice, you can perhaps from a hand wavy point of view, figure it out from the fact that we have a binary system. So we have two black holes orbiting each other. Okay, So if you're thinking about what you see in terms of gravitational potential, so we have a binary orbiting around, you can imagine yourself here as an observer, just watching it. Okay, and think about what the gravitational wave emission the gravitational potential you see at this point. So it is going to be largest when you have one of the black holes or whatever the binary component is opposite you, or the other one, right? So if you're watching it as a function of time, your gravitational potential is going to be a peak as one black hole passes, going to go down, and then you're going to get another peak when the other object goes past. So you're going to have 2 peaks per orbit, one for this object, one for the other object. So 2 peaks per orbit corresponds to twice the orbital frequency for the gravitational wave frequency.
Yeah, got it. Thank you.
I have a question.
Mm-hmm.
Can hyperbolic orbits produce gravitational waves that are detectable?
Excellent question here. Yes is a simple answer, yeah, whenever you have eccentric, whenever you have accelerating masses, as we spoke about right at the start, you're going to have gravitational waves. Okay, we just need Q dot. Okay, so it depends on how much emission depends on the frequency spectrum. Now, if you have hyperbolic motion, so we don't have a bound object, but we have another object coming in. So we have an orbit, say something like this. We have more massive, one object going by, the other object going there. In a particular frame of reference, we're going to have a burst now of gravitational waves, basically, which will looks like something else. So going to peak at closest approach, going to be quieter further away, and here. So yes, this will emit gravitational waves. The question now is this detectable? Okay, so there are a couple of things if we come back to our idea of what makes a detectable source. So we need to be close by, and then we have this characteristic frequency here. So characteristic frequency will be comparable to the eccentric binary, but the emission time scale is much shorter. Okay, so characteristic time scale is just the periapse pass here. Okay, now why this is a problem is coming back to what we were talking about when we're talking about detection and the exact algorithm you need. That when you're looking for a very long signal, okay, you have many cycles. So here's our in-spiral merger ring down type thing. We look for a signal like this, so we get a template, we fit it through the data, and we need to get this to match up. Because this is longer, we only care, so when we're doing the detection, we'll talk about this a little bit more later on, we really just care about the integrated gravitational wave signal. So the number of cycles, the total amount of time, as well as the amplitude. Okay, so amplitude could be the same for this source, but it's much shorter. So when you integrate up the total gravitational wave frequency, you get something that's much less. So it's lower signal to noise ratio for a comparable distance. It's quieter signal, so it's harder to detect. And also because it's shorter, it's less well modeled. It's harder to distinguish from a burst of noise. Bursts of noise often look like this. So this is harder to detect, which means in practice, we can only detect this for close by sources. So this is something which is searched for in LIGO Virgo data. We've not made a detection of this yet, but it is potentially an interesting target. Coincidentally, I did my PhD research on something similar to this, not for LIGO Virgo Kagra, but for LISA, the space-based detector, in the case of having a supermassive black hole and a stellar mass object going close by. And in that case, you could maybe see it in our own galaxy or a few nearby galaxies, but not further away. Whereas if you had the in-spiral of the small object, you could see that to quite large distances.
So this could be a model for some glitches?
Yeah, so it's hard to model because of the waveform. It does look a lot like glitches, but you could potentially still find these signals. It's just harder to find.
Okay, thanks.
You can ask a bit more about this type of thing when we get to the third lecture and start talking about detection in a bit more detail. Okay, there's a question. Could you repeat about the massiveness of stars usually get involved, yes, in chemically homogeneous evolution. So the chemically homogeneous evolution process, you typically need quite large stars for this process to get working. So there's only a sort of a particular mass range where you can get them close enough to be tidally locked and massive enough that they can do the right amount of distortion. So they need a particular mass range there. And then in terms of the masses of the black holes they leave behind, normally when you have a star collapsing down to a black hole at the end, it's basically the core determines the size of the black hole. Outer layers might be lost due to winds, things like this. Chemically homogeneous, as we're mixing things in, we tend to end up with slightly more massive black holes at the end because we're sort of growing our core, we're losing less mass in the sort of fraction of initial mass collapsing down to the final remnant mass is a bit better. So we end up with a bit more massive objects in chemically homogeneous evolution than if we had the same mass star not being all mixed. Okay, so that's quite complicated. We can talk about that a bit more next time, I think. It's maybe a bit too much to go through all those ideas right now. Okay, that was rather a lot of information, I think. So that's probably enough for today. Yeah, if you have questions, drop them in Slack or bring them along to some of the future sessions, and we'll go through some of the more detailed physics, talk a bit more about this relationship between initial mass and final mass. Is a very important point, actually, next lecture, and talk about more formation channels. Okay, thanks.
Okay, do you have a question? Okay, so thank you very much, Christopher, for this excellent kickoff lecture. We will continue tomorrow.